So we're going to look at vectors and coordinate systems. Okay. So we can look at some of the properties of vectors. We've already defined vectors. We already defined vectors and scalars. So let me just remind you of that. We'll say a scalar is a quantity that has magnitude but no direction. So let's look at a few properties of vectors. So the magnitude is the length of the arrow, and the direction is the orientation of the arrow. We can say that two vectors are equal if they have the same magnitude and direction. Two vectors are equal if they have the same magnitude and direction. So an example is vector A, and this is, let's say, vector B. A is equal to B because they have the same magnitude and direction. Okay? And then we can have another vector, let's say A, and the vector B. A is not equal to B since B is longer. And we can have A and B. Let's look next at vector addition. So we can add two vectors A and B. So let's say that C is equal to A plus B, like that. So let's look at the vectors shown below. So we say that suppose we have a vector, let's say A, going this way, and then we want, so the vector represents, for example, an object moving along the A axis, in the A direction, and then ends up somewhere here. This is vector B. The net or the resultant vector can be found. So we have vector A and vector B. So let me put the A at the bottom instead. So vector C is this vector here. So C is equal to A plus B. The angle between A and B is 90 degrees. Okay. So we can say that the magnitude of C, the magnitude of vector C is given by C equals square root of A squared plus B squared. So that's the magnitude of C. It's just Pythagoras' theorem. So if this is C, that is A, and this is B, then the angle of theta is the direction of the vector C. This is 90 degrees. Okay, so the magnitude of C is A squared plus B squared times square root, and the direction of C is the theta equals tangent inverse of B over A. So we can say that in general, suppose we have the following vectors. So let's say we have vector A and vector B, and we want to get vector C, where this angle is theta this angle is, let's say, phi, and that angle is theta. And what we will say is that C squared is equal to square root of A squared plus B squared minus 2AB cosine phi.
Is that C or C squared?
C squared is, oh sorry, C, yes, C. C is the square root of, thank you. C is the square root of A squared plus B squared minus 2AB cosine phi. So we can say that if the angle phi becomes 90 degrees, so this becomes Pythagoras' theorem. Okay, so we're just saying that in general, this is called the cosine rule. So what I just gave you, so this is the cosine rule.
On the C, right?
Eh?
On the C.
Yes, C again. Sorry, keep writing C squared. C is that this is called the cosine rule. Okay. So we have two ways that we can add vectors. We can add vectors by doing so-called tail-to-tip method or parallelogram rule, and I'll show you in a second. Are you all familiar with the cosine rule? Before saying that before, right? Yeah. So let's look at some methods of adding vectors. So we can add the vectors by using either tail-to-tip method or parallelogram rule. So let's look first at the tail-to-tip method. Let's consider adding the two vectors below. So let's say we have a vector, let's say this, we have this vector plus, let's say that vector. So this is vector A and vector B. So we have vector A. So we can add these two vectors by taking one vector and taking vector B and putting its tail on the tip of vector A. So I take this vector, this is vector A, and I put vector B on its tip like that. So this is vector B. So the diagonal from the tail of A to the tip of B is the vector C. So this is called the resultant vector. Okay. So that is one way of doing it. And then we can also, so C is equal to A plus B. So we say C equals A plus B. Another way is called the parallelogram rule. So in the parallelogram rule, we can consider adding the same two vectors. So we have the vector, let's say A plus vector B, and we're going to say the parallelogram rule just means that you create a parallelogram of the two vectors. Suppose, let's say I have it here first. Let's say this is B and this is A. To create a parallelogram, I'm just going to take the vector B and transpose it to this side, and then take the vector A and transpose it to that side like that, and then I'm going to take the diagonal of the two vectors. Let me redraw that. So I do the diagonal of the two vectors like that, and so that creates a parallelogram. So this vector is C. So C is again equals A plus B, and C is the diagonal of the parallelogram. Okay, so C is the diagonal of the parallelogram. Any questions on that? Yeah.
When do we know when to use them?
Want to use what?
When to use
One of these methods. Any of these methods will work. So if I just give you any vector at all to add it, you can always use tail-to-tip method or any of those methods. It doesn't matter which one you choose. They give you the same result, as you can see. Yeah. If the vectors are perpendicular to each other, then you just use Pythagoras' theorem. If there's an angle between them, you use cosine rule. Let's try an example. Maybe that will help. So this one has two vectors with an angle between them. So see if you can calculate the resultant vector.
What's the direction of A?
Hmm?
The direction of A.
The direction of A. They are both, they are both in the same direction. They just have an angle between them. They are both in the same direction. It's just like A is one way, B is the other way. They are in the same direction. So they have, it doesn't matter really, they have an angle between them, just like, if I draw them like this, see, like that, they are just, you see, I have the vector notation on them, so yeah. What is the magnitude of C? We have 2.5. Is everyone getting 2.5? Okay. So C, we have 2.5. What about direction? What? The direction? What did you say?
No, I said magnitude.
What do you
How
have?
could it be lower than the two numbers?
I'm just asking what you guys got. So he told me that.
Oh, okay.
So what do you have? Okay.
9.6.
9?
0.6.
5.
7.81.
9.66.
Okay, so we have several answers here. What about direction? Who has an answer for direction?
19.82 is
19.1?
82.
19.82. Okay. Okay, so we can use cosine rule. C is the square root of a squared plus b squared minus 2ab cosine phi, cosine theta okay. And so what you can do is just plug in the numbers. What was A? 4.7. B is 5.3. And then we have 2 times 4.7, 5.3 cosine 30. Okay. So the magnitude of C is equal to, what do you have for C? What will it be? Is that what you guys did?
I to the plus a square plus b square plus 2ab cos theta.
It's minus 2ab, not plus.
2.65.
What?
2.65.
Okay. 2.65. Okay. Did I give you plus or minus? I'm not sure. What did I give you? I thought I gave you minus. Yeah. So the angle between the two is 30 degrees. So it's let's see. So C equals 2.65. Okay. I guess that's what we're getting.
I believe most of the variations were because we didn't see a pictorial of the two vectors.
Right. Yeah. So I should have given you that before. I think the way my intention actually, I didn't give you the question the way I wanted to give you. That's why it's a bit confusing. What I wanted to do was, yeah, it is confusing because it's my fault. What I wanted to give you was a graph which looked like this. I'll show you in a second. I wanted to give you something that looked like this, but then I put the angle here as 30 degrees, but this should be more 120 degrees. Then it will give you the result, which is what you want, but that was my fault. So the way I gave it to you, the angle is 30 degrees. It's basically like this, so this is what you have. That's why it's shorter.
So if it actually was the other one, it was a 7.813.
Yeah, so it's my fault. I didn't set the question up well, but this is the one on the right is what I gave you, because but when I did the example, I did that one over there. What I gave you here, cosine rule. Why did I put it here? See, so I put phi. You see the phi over here. So that is that result over there. But I was trying to give you a similar. I should have given you the angle as 120 or something. Then you get that. So when it comes to the angle, we shall calculate the angle later. I'll show you how to do that later without having to do the trigonometry. Otherwise, we have to take the trigonometry and do it. So I'll show you how to do that later. Okay, let's continue. Let's look next at, before that, let me make a summary. So both of these methods are actually graphical methods. They are called graphical methods of vector addition. So the next thing is we will put the vectors in a coordinate system. So we shall introduce a coordinate system representation. So this will make it easier to calculate result times vectors and directions. So let's go to coordinate system representation of vectors. So we introduce the Cartesian coordinate system. So suppose we have a Cartesian coordinate system that looks like that, then we can say that this is x and this is y. This will be quadrant 1, 2, 3, and 4. So we have a 4-quadrant system. So we have the 4 quadrants shown. Yeah.
I'm not clear about
The parallelogram rule. Okay, let me review that shortly before we go on. Okay, so let me put here. So we had a question about parallelogram. So we'll go through that shortly. So the parallelogram rule just means that we're going to draw a parallelogram whenever we are adding vectors. Okay, so this means So when we add two vectors, we draw a parallelogram. So for example, let me think of one that we can do. So if I wanted to add, let me do a simple one. Let's say we wanted to add vector A plus vector B. So they are just at right angles to each other. Okay. So we want to add vectors A and B. So this is vector A plus vector B. Okay. So by parallelogram rule, it means that let's say this is A and B, this is A, that's B. The parallelogram rule just means that you're going to take this vector B and draw its mirror image here, and then take this vector A and draw its mirror image there, and then the diagonal between the two is your resultant. So what you are doing is drawing a parallelogram. So you take vector B and put it here, give me a second, something like that, and then you take vector A and you put it there. So this is A, this is B, this is A, and then the diagonal is just from the tail of A to the tip of B, so that would be vector C. So what I've drawn is a parallelogram. Do you see that? This is a lot like the tail to tip method without drawing a parallelogram. So in the tail to tip method, when I had a two vectors A and B, I just do the diagonal. In the parallelogram method, I'm drawing a parallelogram by doing that. So when I get this parallelogram, then I take the diagonal of it. So they are basically the same. It's just that one is an extra step. You know, you can think of another vector. So let's say C is equal to A plus B. So C is the diagonal of the parallelogram. Let's say you have a vector A plus another vector, let's say B, something like that. So this can be written this way. So you have A and then you have B. You're adding them together. The same thing applies. You take the B here and then you take the A like that. You see that? And the resultant is the diagonal between the two.
What about the angle?
What?
What about the angle?
Well, the angle is the same. So the angle of the resultant vector in this case is this angle here. In this case, it will be this angle. You see that? So in this case, it's easy to find an angle because we just use trigonometry. We can do the same here, but we can do the same here, but it will be trickier to do. So we will have to take a component here and then use that to find the angle. Or we can do something called a sine rule. There is something called a sine rule you can use, but I didn't talk about sine rule, so we'll leave that for now. Maybe next time we'll talk about sine rule. Okay, but something like this we can use sine rule to do it. Let me see. We can say that to find the angle. So the sine rule will apply. For example, let's say we have some angle, something like that. Let me see if I can draw it. This will apply to this scenario. So something like this. So if I can, let me see if I can remember. So this is, let's call this A, B, and C. So this will be C, B, and A. So I think it's, let me double check it before I write it out. What is that? Yeah, something like that. Sine A over A, sine B over equal to sine B over B equal to sine C over C. It's like that. Let me just double check it to be sure.
Just that the angles are capitals and the sides are.
Okay, I think I have it. So I have it opposite. So sine rule. Let me see. What is that?
Small a by sine A equals to small b by sine B.
Yeah. So sine, I think I have the letters the opposite way. So you're going to do something like this: sine A over A, and then this should be equal to sine B over B. No, sine lowercase b, I think it is. So if you know one side and one angle, then you can, and also the diagonals, you can do it. But I haven't looked at sine rule. I just want to make sure that I got A by sine A. Okay, so it's, yeah, I think that I have it flipped. Yeah.
It's the same thing.
Yeah. Let me, I know, but let me just double check it and make sure that sine. See, a lot of the books don't have sine rule in them. They have cosine rule, but no sine rule. Let me see. Yeah, so I have it flipped. So A over sine A, yeah. Let me make sure. Let me just write it the correct way. So it's gonna be A sine lowercase b. So you can use that if you know, if you have that kind of setup, you can use that. Does that answer your question?
No, I don't know this parallelogram law in the previous question. Can't we do this question with the parallelogram law?
Well, we can, yeah, we can certainly do it that way. It should give you the same result. Okay, let's do it and see. Okay, so if we redo that program, that problem using parallelogram rule, then what we have is, I think I gave you something like this. This is A, and then I gave you B. The angle is 30 degrees. So by parallelogram rule, you're going to have this, and then you're going to have that. And so your result is this result here. Is that what you were thinking? So this should give you that result. Unless you were thinking, maybe you were thinking it was this one. That's why you are confused. Yeah, no, that's not correct. Because you are going from the tail, you see, you're going from the tail to the tip. Okay, so this is the correct way to go about it. This is the diagonal of that parallelogram. Okay. Other questions on this? Was anybody else confused? I guess I didn't realize that was a confusion. That's why it wasn't crossing my mind what you were asking. I didn't realize there was that confusion. But that is the correct way to do it. Did anybody else have trouble with that? Okay. So let's leave that alone then. Let's continue. We have a little more time. But what we have next is vector algebra, so we can do it. Let's look at the components of vectors next. So vector components. So let's consider the vector A represented in the xy plane as shown below. So we have the xy coordinate system, and then we have a vector A at an angle theta. So we can find the components of A parallel to the x-axis and the y-axis. Okay, so A subscript x is equal to component of A on x-axis, and A subscript y is equal to component of A on y-axis. So we can go here now. This is x, this is y. So this is the vector A, and this will be AX, and this will be AY. The angle is theta. Okay, so we can say that A subscript x can be found. So what we can say that so the vector A, so we can say vector A has the two can be written as AX I hat. No, actually, before I get into AX I hat, I'll do this. Let me just do it this way. AX plus AY. Okay, those are the two vectors, the two components of the vector A. AX and AY, where AX is equal to A times cosine theta, okay, and AY is equal to A times sine theta. Okay, so what we've basically done is to say that the vector A has the two components AY and AX, and the angle between them is theta, and this is 90 degrees. So by trigonometry, we are just saying that AX is A cosine theta and AY is A sine theta. Okay, do you all see that? So those two are called the components of the vector A, and we can certainly use the unit normal vector notation, but I'll leave that for next. So let me finish with the vector algebra before we go. So we can say that with our knowledge of the components of vectors, we can now add vectors using the coordinate components method. So for example, let's add the two vectors A and B below. So let's say that we have a coordinate system like that, and we have the vector A, and we want to add it to another vector, and this vector is at a certain angle theta. Okay, so we have vector A and vector B. We can add it using the coordinate component method by taking each vector individually. So this is vector A, and then I'll take vector B by itself and put it here with an angle theta. Okay, so each of this is going to be y and x. So I can say that vector A has a component A subscript x. Vector B has the component bx plus by, and so the resultant vector C is equal to vector A plus vector B. Is everybody following that? So we can say that the resultant vector C has the component x. So we say Cx is equal to Ax plus Bx. Cy is equal to Ay plus By. And so we can say that the vector C is just the square root of Cx squared plus Cy squared, like that. Okay. So here, if you like, we can say that since we know what Cx is, let's look at A. So now looking at vector A, vector Ax is just equal to vector A. Vector Ay is equal to 0. So we can say that vector Bx is equal to B cosine theta, and vector By is equal to what?
B sine theta.
B sine theta. Okay, so we have Ax, we have Ay, we have Bx, we have By. So now we can find Cx and Cy. Okay, Cx is equal to A plus B cosine theta. Cy is equal to 0 because there is no Ay, plus B sine theta. So this will just be equal to A plus B cosine theta, and this is equal to B sine theta. So once you know Cx and Cy from those two, then that's when you calculate your resultant vector C. That will be just Cx plus Cy. You are squaring it, of course. And then the direction of vector C is just found the way we talked about. So the angle phi is just the tangent inverse of, what will it be?
Cy over Cx.
Cy over Cx. Very good. So that's the way you do the coordinate component method of vector addition. And this will work for any number of vectors also. We are almost out of time, so what I'll do when I come next week is I'll give you some examples of different vector orientations that you can use with this one. Okay. Questions at this point? Okay. So that is it.